This is an introduction to exercise 17C on approximating the distribution of a sample proportion. So when, we talked about this earlier, when the sample size n is large, so when n is extremely large, this sample proportion p has an approximately normal distribution. And we can refer back to the normal distribution approximation we had at the end of the last chapter, where we said if the probability is closer to 0.5, or 50%, and the n value of the sample size is extremely large, the larger it gets, or the more close to 0.5 our probability gets, the more similar our distribution is to a normal distribution. And our mean is calculated by just the probability of our, mean of the sample proportion, there we go, is calculated by the probability, whereas the standard deviation can be calculated by just finding the square root of p times by the probability of failure divided by the sample size. In this example, we're going to go through using a ClassPad calculator. Please make sure you take it out in the meantime. So for example 40, we have to assume that 55% of people in Australia have blue eyes. Is that true? Absolutely not. But we'll pretend that it is. Assume 55% of people in Australia have blue eyes. Use your calculator to illustrate a possible distribution. Remember that your answer is likely going to be different from someone else. Of sample proportions p hat that may be obtained when 200 different samples, each of size 100, are selected. Okay, so 200 different samples. So we're saying if I grab 200 different samples, and again they're random samples, so we're assuming that they're going to have very similar ideas. And we said if each one is 100, what is the probability that however many people, or what is the probability or the average of that amount of people having blue eyes? So in your calculator, we're going to open up statistics. Here we go. So you're going to go to, well, I'm going to clear this one first. You're going to go to statistics, and at the bottom of list 1, and more so just above the scrolling bar, there's a calculation cell. So imagine that's like your Excel document when you press equals in the cell and you put a formula in, same idea. You can put that in, and then just like before, you go to keyboard and catalog. Am I going too quickly? Okay. Go to keyboard and catalog. I'm going to put in the data that we need. So in this case, we're going to put in a rand bin. That's this one here. Make sure you click it so that actually goes in. You're going to put in your data. So the parameters set, as you can see on the right over there, is the sample size, population proportion, and number of samples. So the sample size, of course, is going to be 100, because that's how many people in each sample. The population proportion is 0.55. Keeping in note, that's the population proportion. We don't know the sample proportion, of course, because the sample proportion is specifically out of those 100 people we select, whereas the population proportion is out of the whole thing, which we know is 55%. And then finally, for a number of samples, it's going to be 200. Now, to calculate as a proportion, right, because right now if we put this in, it's going to give us, for example, let's say 57 or 58, right? To calculate as a proportion, we can divide by the sample size to get as essentially a fraction, right? So for example, instead of 58, it's going to be 58 over 100, or 0.58, so that would be our probability proportion. So we go divided by 100 to get our sample size. Don't forget your bracket. And you hit enter. This one will take a while, unfortunately, but it will give you a bunch of numbers. My one's probably going to be faster than yours because it's using my laptop, but you get the idea. Okay. If you would like it as decimal or a fraction, whatever it is, just make sure you set the standard decimal option at the bottom. Just hit enter again. It should give you your values as a decimal or fraction as you see fit. Of course, if I scroll down, it should only go up to 200, right? Because we've selected, or we've gotten 200 different samples. And for each one, you see that each value should be about 0.55, right? If we have anything like above 0.7 or 0.8, that's likely going to be an outlier. Or if it's below 0.4, likely an outlier, right? But you can see that for each one of these cells, it represents 100 individuals in a sample, and what that sample proportion is. So for example, in cell number 2, 0.54 means that out of the 100 people we picked for that specific sample, 54 of them, or 0.54, sorry, of them have blue eyes. Okay, so that's what that means. If we wanted to represent this as a graph, we can actually just go to, well, actually the first thing we have to do, for those of you that do further know this as well, we have to set this. Okay? The button is right underneath the diamond, and basically it's just saying what we want the information to be interpreted as. And I'm going to get it to be interpreted as a histogram, kind of similar to our binomial distributions. Set that to a histogram, and just double check if you have named, or if you've got other variables, whatever it is, just double check you've got the right column. In this case I haven't named it yet, so I'm just going to use list 1, and just hit set. Nothing's going to happen, because we've just told the calculator how we want it to interpret the information. And then you click the top left button. Now, what it does, it spits out some numbers that it feels like would be an accurate representation. I don't particularly like this. I'm generally speaking quite happy to start at 0, but in this case, I think looking through the numbers, there's not really any of them that are below 0.4 really, because that'd be quite unlikely, wouldn't it? In fact, I would say guarantee none of them would be below 0.3. Let's put 0.4 as our start. So instead of starting from 0, having a massive gap and then going up, let's start at 0.4. The step indicates the width of each one, so the interval size. And so let's say in this case, I wanted my interval size to be, let's say, 0.01. Right, so I'm going to go up in intervals of 0.01. Okay, and it should spit out a graph that looks something like this. Right? And you see it is approximately a normal distribution. Any questions about that? If you would like to calculate, you could go to calculate, and then because we're working with a single variable, click calc one variable. Again, double check the list 1, or the name of your list is the information you want to use, and it would spit out these numbers here. X bar, you guys know, means what? Average, thank you very much. Now, here's the question, right? I don't know if you guys can see that up the back. There is a sigma x and an sx. And then the two numbers are very, very, very similar, but they're slightly different. Does anyone know what the difference between them are? They're very similar. And you can see they're only 0.0002 off, but the sx is the standard deviation of the sample size, whereas sigma x is the standard deviation of the population. It's a very small difference, and for us, we're going to be using sigma x for the majority of it. Just keep that in mind, don't get that mixed up with sx. They're going to be very similar values almost all the time, but sigma x is what we're going to be using. And then, of course, you guys know what median, minimum, etc. You guys know what that means. So you can see, for example, the smallest value is 0.42. And if I was graphing it, I wouldn't want to go from 0, because the small one's 0.42, sorry. Any questions about that? Generally pretty happy with that? Awesome. Let's jump into the next question. So let's scroll down and look at, look down, sorry. Example 40, that should say 41. Assume that 60% of people have a driver's license. Using the normal approximation, again, normal approximation, find the probability, or the approximate probability, that in a randomly selected size 200, sample size of 200, more than 65% of people have a driver's license. Let's define what we know first. I know that n equals to 200. I know that p equals to 0.6. Of course, we're assuming that because n is so large, that the distribution of p hat is approximately normal. So in that case, we say that the probability equals to the average, which is 0.6 for our distribution. And of course, using the formula, we know that sigma equals to the square root of our probability, multiply probability of failure, divided by 200, which is our sample size. This will give us approximately 0.0346. Have I gone too quickly at all? Okay. So what we're looking for is that we're finding the probability that p hat is going to be greater than 0.65, aren't we? It's more than 65%. There's a couple of ways you can do this. We could go straight into the calculator and say, all right, let's go to our main. We'll go to interactive distribution. I'm going to use a normal CDF because remember, we're assuming it's a normal distribution. It's approximately. And we're going to put in our value. So 0.65 for our lower. And we'll put in 1 for our, I guess we could put in infinity, sorry, for our upper. Our standard deviation is what we put in earlier, so 0.0346. And of course, if you're using your calculator for this point, which you should be, make sure you try to copy as many decimal places as you can, or just copy the value itself into this section for the standard deviation, and your average is 0.6. And it'll give you an answer of 0.0742. Alternatively, we could also change this to be in the probability of x being greater than 0.65 times by our sample size. So we're saying that the value of x, instead of looking at the proportion, we're saying how many people in that sample size of 200 are going to have a driver's license. And we're saying that we want that number to be greater than 65%, which we know to be, if we put in the calculator, probability of x, that's not an x being greater than 130. In this case, our standard deviation is going to be slightly different. And we end up with a very similar answer of 0.074 as well. Okay, but this focus here should be that if we can have a value where the sample size is extremely large, we can assume that the average equals to our probability, and the standard deviation follows that formula that we already know as well. We can plug that into our calculator using normal CDF and calculate that as we see fit. Any questions? Okay.